back to another video. It's been a while. It's been, I think, about 2, 3 days that I've uploaded a video. I'm extremely sorry for that. I've had some other things going on, and in the midst of all of this, I found it a bit difficult to find questions and then upload. But I promise I'll try to be more regular from now onwards. So here, this is a question from the IB Chemistry paper to HR from May 2017 times on one, and as you can probably tell, it's from topic one. And I know that I set out stop topic one videos a while back, but I feel like I haven't covered some concepts. And this is one of the very important concepts that comes up in topic one. And this comes up in almost every single exam that I have written. And that's not an exaggeration. That is actually quite the truth. If you even go to different papers and if you scroll through them, you'll see that such questions come up in one form or the other. And they are worth quite a bit of marks. 2 marks, that's a lot for a chemistry paper. So this question is asking us, titanium exists as several isotopes. The mass spectrum of a sample of titanium gave the following data. So what are isotopes? Well, in very simple terms, an isotope has the same number of protons, but different numbers of neutrons. And thus you can see how the mass number is changing because neutrons also contribute to the mass of the atom. So as the number of neutrons changes, the mass either increases or decreases. And elements can have different isotopes, meaning they can have different elements, or they have different atoms which have different number of neutrons from each other, but at the end of the day they are the same element. They are titanium, for example, but they just have slightly different identities to each other based on the number of neutrons. You could think of it like the human race, right? The human race is so diverse. We have people from different countries and from different races and nationalities and religions. You could think of it like that. So we're, at the end of the day, we are all humans, but we are distinctly different from each other, just like this. These are all titanium atoms, but they are distinctly different from each other, and they're separated by the fact that they have different number of neutrons. Hopefully that analogy would help you understand this concept a bit better. But now they've asked us, calculate the relative atomic mass of titanium to do the two decimal places. Now they're asking us, even though titanium can have these different identities, we need one standard relative atomic mass of titanium because each isotope of titanium has a different mass number, right? So they have, one has 46, one has 47, one has 48, one has 49, one has 50. So they're asking us, how would you calculate a relative atomic mass, a standardized value for titanium? You could think of it like the average. You can think of it as if you were to randomly select a atom of titanium, what would the most probable answer be of the mass of that titanium atom? You could think of it like that. And another thing that governs this relative atomic mass in order to calculate it is the percentage abundance of that specific titanium atom. So for example, if you were to look at the human population, and if you were to randomly pick out one person from the human population, approximately the chance, the 1/7 chance would be of you picking up a person from India, because India has a population of approximately 1 billion people. There are about 7 billion people on Earth, so 1/7, there's 1/7. So you could say that the percentage abundance of Indians on the Earth is around, let me do the calculation, I didn't prepare for this, is about, it's about 14%, right? It's about 14 or 15%. And just like that, you have this, where different identities or different isotopes of titanium have different abundances. So some are more abundant than others, while others are less abundant or the same. And as you can see from this, 48 is clearly the most abundant isotope. So that means if you were to get a block of titanium and if you were to scan all the atoms in it, you would probably find a majority of 48 titanium in there, titanium atoms with the mass number of 48. that would be its percentage abundance. It's most likely to be found, and it composes majority of the titanium that is found on this earth, or that we have found. Now, how do you determine the relative atomic mass using all of this information? Hopefully, I've explained you the terms and definitions well, and hopefully you understand what I had been talking about. Now, how do you use this data to calculate the relative atomic mass? It's a very simple formula. You have to first look at the mass number, which is 46, and you have to multiply it by its percentage abundance, which is 7.98. And you have to do this for every single one of the other isotopes of titanium, and you have to add them together. So 46 times 7.98 plus 47 times 7.32 plus 48 times 73.99 plus 49 times 5.46 plus 50 times 5.25. And we have to divide this whole thing, divide this whole thing by 100. And if you put this into a calculator, you will get the answer as approximately 47.93. So the answer to this sum is 47.93. And this is the relative atomic mass of titanium. So this would be our answer. Hopefully you have understood the formula and how to do it. That is it for this video. It's a very simple concept, very easy to understand. I'm sure all of you are extremely intelligent, and all of you will be able to understand this concept. Thank you so much for watching this video. If you have any other questions regarding this concept or any other concept, please feel free to message me. I will do another video tomorrow based on mass spectrometry and isotopes as well. So stay tuned for that. And that's it. Feel free to reach out to me with any questions you have. I'll be more than happy to help you. Thank you so much for watching. I'll see you in another video with another question. Take care of yourselves. Goodbye.